welcome to the 75th session of the Porous Media Tea Time Talk. As many of you know, this initiative was created within the Interpol Young Academy to provide PhD students and postdocs with a platform for knowledge exchange and bring their work to the global Porous media community. And this series has grown into a vibrant, supportive space for scientific exchange, and we are now reaching this 75th session. And this truly reflects the enthusiasm and commitment of all of you who join us month after month. And to mark this milestone, we are thrilled to host a special session, and we will welcome back 3 of the original co-founders of the Porous Media Tea Time Talk, who are now leading scientists in their field. So please join me in welcoming Kamaljit Singh, Tom Bultreys, and Maja Rücker, which should be joining soon. So this is for you the perfect opportunity to not only learn about research of this inspiring person, but also to reflect on academic journeys and community building. So engage anytime, ask questions and drop comments in the chat. And in this sense, I would just like to start the session by giving the stage to our speakers and have some chat about how they feel returning to the studio as speakers. And so could you tell us what your early days as PMTTT members brought you, personally or professionally? And if you can give some advice to your younger self from this time, what would it be?
Well, thank you very much for having us here. It's really a pleasure and honor to be part of this webinar series. And it's very interesting to be this side now as a presenter, fully nervous. Then before, on the other side, when we were host, again fully nervous whether this actually is going to be okay or not. Now it's been a great journey throughout. We started this PMTT with all of you guys, and that time I think it was neat that we didn't have many conferences, and then it was a great platform to interact with young researchers, different topics, and in fact it gave a lot of, because it's recorded, it gives us an opportunity to go back again if we want to see, so we miss few things or we want to revisit some of the great research people have done. And it's been really good community and interaction from my point of view. And it was nice that it was absorbed into Interpol, and which got then more heights, and then it's advertised in wider community because Interpol has a wider circle. And it's really a great feeling to be part of this, yeah. So I took everything most Tom.
Yeah, I second that fully. It's a great honor to be invited by you guys, and I mean I must really also put the spotlight on you guys, right? The organizing committee, also people that used to be in the organizing committee but have left by now. I think when we started this, we had no clue that it would last that long. I think we were hoping it would last for the few weeks that we thought Corona would take in the beginning. So it's really a great pleasure to see that you guys have picked this up and brought it this far. Yeah, and for me, it's been an important platform, especially during Corona. Like Kamal said, there was a big need at the time, but also it's just nice to collaborate on this with friends. That's been really great. And I think also on a professional level, it's something that also stands out, right? Because these are kind of initiatives that, not everyone has on their CV. So I think that's on a professional level. I mean, I've had the comments from people screening my CV saying, oh, this is something that I really noticed standing out. So, I mean, we didn't start off with it thinking about that, but in the end, that's also nice, I think.
Yeah, it's been very positive, I think, for all of us. And what you said, Tom, like this, professionally, of course, it counts for us as organizers. But I also got to hear from a couple of people that were speakers before that it was important for them professionally, like when they applied for postdocs or for jobs outside of academia, that they could show there's a presentation of where I talked about my work online, and then the next potential employer could have, not only the written CV and the papers, but to just see how you could communicate, how you could present. So this counts very positively. We heard from a couple of presenters from past sessions also that it was nice for them to have on their CV that somewhere they had presented online and people could see that. And I have to say that I'm really surprised, very positively surprised that we got this far, because I don't think anyone could have imagined, right? I mean, like Maja started pitching the idea like to me and to you guys, like having like getting together to organize this online series of talks. So during the pandemic, since Interpor and so many other conferences were being shut down, so lots of people, for the established researchers, it's bad, but it's okay, right? They are already known, so they are invited for talks by their peers and such. But many PhDs and postdocs in early careers, they do not have like a solid name in the field yet, so they needed a place to present. And then we came up as this potential outlet for that, and that's we had enough momentum to continue after when conferences became regular, and that this leaves now as an instrument by itself. I think it's really amazing, and I could never have anticipated that would happen. And also, like I was like scrolling the other day through like the past sessions. I think what we have is a really good snapshot of the global picture of porous media research in this period, in the beginning of this decade. Because if we just see like more or less what people are doing and where, we really have an idea of what the field is and how it's evolving. So I think that was another positive contribution that we got. Oh, I see that Maja is coming here into play. So maybe we could take the chance to welcome her on the stage. If I may, I'll just join you. Hello, Maja. Hi.
Maja, you're live.
And hear us? I'm not quite sure if she is getting it yet. So, okay, let's take a little bit of time for Maja to fix the situation.
In terms of Sarah, you asked like some career advice session. I got one slide as like you have suggested to put for all the speakers. And,
so let's keep that for later then.
Yeah, although the discussion on those points about the work-life balance, which is an important part of research, it can be hours. But I will give my thoughts for one slide within 2 minutes, plus maybe like what I did to improve it slightly, because I was suffering from, like many other researchers, work all the time. Even you go bad and then you're thinking about research, not like other jobs. Okay, I'm not saying the other easy, but sometimes you can shut down and then you say, okay, next morning is a fresh start. And here you got a lot of things going in the mind every day, weekends. And I've got one like suggestion. Maybe people have already using. I learned it very late, probably, but I would like to share that.
I'm very interested to hear that.
Yeah, really looking forward to some advice. And I think this is really important again for all the early careers that researchers attend the session, just to see that how much involvement and can bring lots of positive things, both from our side as member of the team and from the speaker side when they get involved and present their research. So that's really cool to hear some such feedback from you. Thank you very much. So I guess we will go back now to the formal steps of the session. So let me introduce our first speaker. And it's my pleasure to introduce Kamal. Most of you know him, but he's an associate professor at the Institute of Geoenergy Engineering at Heriot-Watt University. And he leads the DG Power Flow group there. So his research focuses on 3D imaging, modeling of fluid flow in porous media, with application ranging from subsurface hydrogen, CO2 storage to biological systems, including termite mounds. And he will talk today about flow heterogeneous porous system from both imaging and modeling perspectives, and dive us into the challenge of scales. So Kamal, again, that's a pleasure to have you on board today. The floor is yours once your slides are ready.
Thank you very much, Sarah, for this kind introduction. I think my slides have disappeared probably, right?
That's
For
true,
some
yes.
reason. Let me not, I think this is not the right one.
I think it's really good that we have technical problems because it shows life how it is. It's the reality of it. Okay, here it comes to our slides.
Here it goes. Yeah.
Can you see the slides now?
We can see it. Thank you, Kamal. The floor is yours.
Fantastic. Yeah, sorry for the hiccup. I don't know why it disappeared. Again, thank you very much for this opportunity. And like I said, it's really a pleasure to be part of this this webinar series. Today, generally I don't do, but I put all the points which I promised to deliver. I'm going to mostly talk about imaging and modeling of flow in heterogeneous system. Could be single phase flow or two phase flow. And then very briefly, I'll talk about upscaling or downscaling maybe of flow in porous system. And then, like I promised, I would put one slide on work-life balance and my experience in this. So majority of my first part of talk is gonna be related to a few projects we are doing on underground hydrogen storage and aquifer, where you inject hydrogen cyclically. You inject, take it out like a temporary storage. Another project I'm going to talk about CO2 storage in hydrogen is reservoir rocks from Malaysia. And then I will briefly talk about other projects related to termite mounts, which also offer quite challenging scales in heterogeneous system. And the common things been along with all the projects is 3D imaging. So we are doing 3D imaging at multi-scale imaging of porous systems, and then using the tools, sort of like similar tools for modeling flow in either subsurface flows or related to termite mount, which I'm going to discuss later. And what I'll do, I'll start with the hydrogen project on homogeneous system, simple system, and then we built upon complexity in the system. Here is the first project we did. Zaid was a PhD student that time, so we took a rock sample. This is a vertical cross section, 2D cross section of a bent hammer, which is a sort of homogeneous sample, and black is the pore space, and these are grains. We fill it with water, and then we inject hydrogen. And then you see on the left-hand side how the hydrogen looks like. And then we take it back, like the first cycle, and this is the hydrogen which is left behind here. Different colors, they are arranged according to the size of the clusters here. And the plot shows here what's the saturation along the height of the sample. This is the saturation on x-axis, y is the sample height. And what you see, this one, the distribution after drainage means after injection of hydrogen. And then blue is, sorry, this is the drainage, blue is the drainage, and this is after imbibition when you take it out. And you can see the distribution, like the extraction or the recovery is more or less uniform throughout the sample. But then we move on to a bit more complex system where we found samples with the layered heterogeneity. It's not the pore scale heterogeneity we're talking about, there are layers here. So this is again the empty space with larger pores, and these are the smaller pores in between, then larger pores again. And when we fill it with water, inject hydrogen, and then we can see that we see here quite a lot of differences here. The middle layer with smaller pores is completely bypassed during hydrogen injection. And this has consequences on the distribution after imbibition, means when you take it out, the hydrogen from the system. And now interesting part here is like when we're talking about large scale modeling, all this pore space here, like the difference between these permeability and pore sizes, they are taken as an average property. So you generally don't consider the fact of this small layer, small size difference here. But if you see at the microscopically, we see the differences that the layer doesn't want to get invaded by hydrogen here. So, and then we moved on to increase the complexity or heterogeneity in the system. And then we said we would like to do on carbonates. The carbonates, they bring heterogeneity in the system in a way that, let's say, this is a horizontal cross section of the sample, and then black is the pore space, and white is grains, solid grains. But then there are a lot of different gray scale of the grains here, and these are grains with intragranular porosity. That means they have nanoscale pores which are connected to the larger pores, which bring some complexity in the system. And here what you see, what we did the same thing, fill it with water, inject hydrogen and extracted the hydrogen. And what you see here, the purple, is the trapped hydrogen after imbibition. And you can see that there's a lot of, it's not homogeneous anymore, and you can see the distribution changes from bottom to the top. And what we're trying to relate this saturation to the structural heterogeneity in the system here. Then we increased the complexity a bit more when we were working on Malaysian carbonate from reservoir rocks. And what you see here, the sample on the left, these are 1.5-inch diameter, which is 38 millimeter, standard core plugs you get from industry. And then one location to other, you can see the complexity in the pore space, not complexity, change in structure, let's say heterogeneity in the system. But when you zoom into, let's say, one of the sample location, it could look like this. This is a vertical cross-section, 2D cross-section, although this is a 3D image. And now the interesting thing here is black is the pore space, but it's not connected from top to bottom. The connectivity occurs through nanoscale pores with the intragranular porosity. So this brings more complexity into flow. For example, if you're injecting hydrogen or CO2, it will go through the bigger pores, but then it stops, and then it has to go through the microporosity and then invades all the pores. We did a few experiments on this, like drainage imbibition, fill it with water, injected CO2 from the top, and then injected brine to see the trapping. And this is the initial results we have. This is what we plotted. Initial saturation after drainage when we injected CO2 versus the final saturation. These are called the trapping curves, the residual saturation after imbibition. And you can see different sample, they all scattered all over the place. And the interesting bits are here, near to the one-to-one line means, like for example, this sample, whatever is injected after drainage, it gets trapped in the macropores, not in the micropores here. So this is like a lot of, it's nice because it's high trapping, but if you're talking about hydrogen, it's bad because we want to recover more. Yeah. So we're looking into that and we're trying to connect it to heterogeneity in the pore space, microporosity, as well as the connectivity of the pore space. If you can come up with some solution or general answers related to that. The second part what we're doing here is looking into upscaling or downscaling, whether, for example, if we can use the experimental data or modeling data from this sample and predict the properties, the macro scale property, which are mostly related to relative permeability and capillary pressure relationships here. And for that, we developed a protocol. For example, we developed a simulator at micro scale, which uses the information from the nanoscale. It gets fed into that, and then we compare the results from those micro scale experiments. Similarly, we have a model which gives us macro scale properties and then uses the information from smaller scales, but then we compare against the experiments, core-finding experiments done on the larger samples. This is again, like we are wrapping up things here, but then one of the things which the nice thing came out of this is the simulator we developed for complex rocks. It's called Extensive Pore Modeling, XPM, which is available on GitHub, open access. And what it does, we go, let's say this is the pore space, whichever is visible, we make it into pore throat, standard pore throat network, and the rest, which is in the microporosity, nanoscale pores, and we use as voxelized image and then convert into Darcy nodes, and we connect them together to run simulations. For example, in this case, this is a window how it looks like. It's very user friendly. You can unclick, let's say, Darcy node, whatever you see is only pore throat network standard, and then it's non-wetting phases invading. We can bring it back with Darcy's node on top of it, and then we see how things are getting invaded. At the same time, we can get live curve with the capillary pressure saturations, and when we develop, also we can click on relative permeability, how it looks like. We started with let's say 1 microporous phase, but as you see from previous examples of 3D images, there are many different grayscales. So the beauty of this one is we can give those different grayscale, different properties, flow properties, and embed it into the XPM and can give you Ralph curves and also saturation profiles, and also, sorry, excuse me, with the saturation, capillary pressure saturation relationships here. One thing we used here very recently in a project led by Josh, And we're looking into using XPM and also combining with the machine learning, and is developed Ensemble Smoother with multiple data simulation approach. For example, in this case, what this slide shows here, this is again large scale sample with 35 millimeter in diameter and 60 centimeter length. We segment into, let's say, pore space, which is 0, visible pore space, and the macro porosity, which is different grayscales. We can, let's say, segment in this case 3 different phases here. And we can use this to run multiple simulations with different parameters. In this case, we ran on 300 cases. And then we can run machine learning dense neural network on it. And it gets trained, and then the results, in this case, we also predicted few relative permeability data points from the larger scale. Another thing Josh has combined with the Ensemble Smoother with multiple data assimilation. What it does, it allows us to infer properties, flow properties of these microscale phases, microscopic phases here. Another thing which also it gives us nice information about that which of the phases need more information. Let's say we might need more drilling of the samples, more nanoscale information. So it gives us nice information which we use for improving the predictions. So this work is also in progress. So Josh is writing up a paper on that. So far what we looked into heterogeneity in the pore space, which affects the fluid flow. But then there's another angle, heterogeneity in wettability, for example. We've done some work previously on looking into flow patterns, but most recent work we are looking into, CJ is leading this project. We're looking into microbial interaction during underground hydrogen storage, because microbes can interact with hydrogen, can create biofilms, and it can change the wettability of the system. So at the moment, CJ is working on the batch experiments where we got reactor, and then also mass spec in line with that. We can analyze the gases, and the ultimate idea is like then move on to imaging experiments where we can look into wettability and fluid flow properties, heterogeneity in the pore space caused by, let's say, the wettability. Okay, so I'll move on to the next topic, which again has multi-scale nature about termite mounts. You might have seen these sort of mounts, and it's been recently in our paper from Nangi. She has reviewed quite a lot of nice work on it. The motivation here, if you look into the temperature outside, it could fluctuate in day and night, but inside it stays plus minus 2 or 3 degrees centigrade, because the queen stays stable, it needs stable temperature, for example. And the motivation here is like, if we understand how the structure of the mounts give nice control of temperature and ventilation, then we can hopefully use those mechanisms to design energy efficient buildings. A few years ago, we published some work related to looking into the microstructures of these termite mounts. So these are like yellow is where termites move around, but we were focusing mostly on the walls. And you can see the structure of these walls here, larger pores, smaller pores, and we would see how they affect flow, CO2, ventilation as well. Then we moved on to quite a lot of extended version of the project. Nangi is leading this as a PhD student, and she did field work in Nigeria. And then you can see a lot of probes sitting into these termite mounts. We're measuring temperature, humidity, CO2 concentration, wind flow inside, outside. And then what we do, we take these mounts and cut into pieces, unfortunately, and then we do medical CT scanning, and then you can see how the mount looks like in 3D. And then Nangi also did a lot of sampling from the walls, which were scanned in Ghent for microstructures. So we're building a multi-scale model, very similar to the processes that we described before. Here, what we are interested in looking at CO2 concentration, temperature, and how these are controlled ventilation and the temperature here. So this is also a work in progress. Hopefully soon we'll have some results related to that. And then if we can understand the mechanisms, then we can go to the next problem with optimizing designs, new type of designs. Well, I think this is all about technical, and then as hopefully I'm not over time, I promised that I put one slide on work-life balance, because we got very high intensity research environments for starting from masters by research or doing undergrad research projects, all the way to academia. And all the thing, like I said before, we always thinking about research sometimes, and there's no shutdown. Maybe some jobs, they will allow you to breathe. And here we're talking mostly about thinking about papers, next proposals. As you go up the ladder, then you're thinking about funding, then teaching duties come into play, admin roles, community, and this is a never-ending list. And what it does actually, it just blurs the boundary and then goes into personal time and personal life and mental stress. And sometimes we got failures and then things go wrong, and which is again affecting the mental health. Like I said, and this is a topic, is very interesting topic. We can talk hours about it. But then I was thinking, they put on one reflection, what I experienced, when I'm doing work, I used to have a to-do list. It's like 10 tasks to do. And then I have like calendar activities full of meetings here and there. And then my evenings were booked trying to finish the to-do list. Then calendar activities was like daytime during the work weekdays. And there was like, again, weekend was sometimes like occupied, which I have recently changed actually. Surprisingly, it's working okay, well so far. Let's see how, hopefully it will go long way. So from my experience, what I did, I removed the to-do list in my, because I had different sheet. I said, okay, let's get rid of that. And what I'm looking into my calendar for next 2 weeks or 3 weeks. Based on the priority I had in my to-do list, I put those things into calendar. And I need to do during this time, that's it. My calendar is blocked. In this way, I totally got rid of my to-do list. And whenever a task comes, it goes into my calendar, and that freed my evenings, that freed my weekends. Sometimes it's okay, yeah, there's urgency, you need to send one email on the weekend, for example, but at least then it's not like over-occupying my brain all the time. And it's been going well so far. So this is the one thing we just wanted to point out, that it's really important to do this work life, like free your evenings, free your weekends, do some activities. If you like to go to gym, or if you like going walk, doing art and craft, maybe, or any social activities, then please do spend time on that. With this, I think I'll wrap up. What message here, I think you all probably know that heterogeneity, either in pore structure or wettability, it is really important. But how to characterize that heterogeneity and linking it to flow dynamics is complex, and where people are working. Second thing, people are working on upscaling or downscaling, and then this is a major task for systems which are not homogeneous. But with the new techniques like machine learning, AI, we are actually doing trying to get more information about upscaling and downscaling. And the last but not least, super important, is well-being, and doing the work balance, that we are not over-occupied with things, and the research, and spend time wisely on things. With this, I think I would like to just highlight the work I showed today is a part of many people in this picture. This is the overall group we have, DG4Flow team. And these are our beautiful sponsors who actually sponsor the work, some of the pieces I showed today. With this, I think I would like to wrap up, and then I'm ready for any questions. Thank you for your patience, for listening to me.
Thank you, Kamal. That was super. We covered quite a lot there. Very nice. Thank you. So I want to remind the audience that they can type in questions anytime on the chat, so we can can ask them to the speakers, and we can also bring questions at the end of the session if you happen to think of a question for Kamal, in the meanwhile. But while we're going, I just have one quick question myself about the science, and we can discuss the other things after. So with the hydrogen experiments, can you just remind me? We've been discussing these things a little bit. Is it pressure driven or flow driven?
These are all the experiments. This time I showed, yes, these are mostly flow rate driven. So
flow rate driven.
We keep the constant flow rate, and then we let the hydrogen to flow at that constant flow rate.
So this middle segment, when you have the lower porosity, the average velocity there increases, right? Because of
Yes.
of a constant flow through a smaller pore cross-sectional area.
That's true, yeah. And also the interesting part here is like middle part, because it's a hydrogen non-wetting phase, it goes, and it stops there. And then starts to accumulate on the top of it. Then it gets a breakthrough. And then, yes, you're right, the velocity is going to be super fast into this smaller regions. And then it breaks through to the lower layer, yeah.
Right. Super. So we have one question here from the audience. So I just bring it up to the screen from Ike Tyson. Which microbes are you using for the hydrogen wettability experiments?
Oh, well, so this is good questions. I wouldn't know the name at the moment, but CJ is the expert in this. But we're looking into two different types of microbes, surface reducing, and also looking into like methogens, like breaking down into looking into if they are forming methanes. So these are at the moment like we like cultivating them and trying to prepare for the batch experiments.
Is it a consortia example from reservoir samples or single microbes?
Yes, we wanted actually to have real samples from our sponsors, and it's always like very challenging sometimes to get the real sample. I think Tom has done some experiments with the real samples. We're very fortunate, but we are using like model systems at the moment. Yeah.
Right. So do we have more questions from the studio, maybe?
Yeah, I will have one. So I was super interested by the termite mounds example. So because I feel like nature-based designs of this type are already quite well optimized for thermoregulation. So my question would be, do you think your optimal design would bring you something highly different, or do you have any idea what you would expect there?
Yeah, I think yes. I think that it will be very different design. For example, if we look into the microstructure or even the larger structure of termite mounds, they look very different, and probably we don't want to live in those sort of structures. The next challenge will be first. I think once now Nengi, what she's doing all the simulations, and the good thing we got field data on the termite mounds we can compare against. And then the second challenge is going to be optimize and try to find designs. And Nengi is writing a fellowship or proposal on that. And then designing, based on this information, designing and optimizing the design. And then come to the third part of like preparing some sort of prototypes. And that's also part of the plan related to that.
But maybe I got it wrong, but I thought you were trying to use this as like isolation material mainly, or do you like thermal local material?
That's the two motivations here. One is design of new type of building. Second is designing a new type of material, which has could maybe property related to what we see in the termite mounds, and having, let's say, thinking about self ventilating bricks, for example, and which has thermal capability, which can give thermal insulation. So this is second motivation behind this.
Okay.
Yeah.
Cool.
And I
Very
think with the
interesting.
3D printed media, so it opens up new corridor that we can try different materials and we can control the structures. Either the problem would be like doing multi-scale with microstructure and looking into making brick blocks, but could be that we optimize the design in a way that we live with not nanoscale, microscale, maybe millimeter scale features into those structures.
Interesting. Thank you.
Super. Any other questions? If not, I suggest we move on to our second. Oh, okay. We got one quick last-minute question here. So thank you for the insightful presentation. Based on your microscale observations, do you envision these breakthrough findings being upscaled to the Darcy scale using mobile, immobile conceptual models? This is from Rima Manik.
Yes, thank you for the question. Yes, so this is what we are looking into now. We have been doing this pore scale research for last 10 years or more, and the question comes sometimes: so what? What about the larger scale? And this is, we've been trying for the last couple of years, upscaling of, or if you know the property at large scale, can we downscale and learn about the nanoscale information? Yes, this is the whole idea now, looking into using the information from the small scale, predicting the flow. And very challenging topic, I would say. But that's what we are looking into, not conceptual models, but yes, you can make models using the machine learning AI so that the runtime is not, because majority of the time we got modeling tools, they are expensive computationally, and then idea is like to develop something which are proxy models or surrogate models. Yeah. But this is the vision, not to go too large scale at the moment. Vision is there, go from like nanoscale to, if we can do inch scale samples. This is the first thing we're doing, and then we have got some proposal to go larger scale. Yeah.
Right. Super. Thanks a lot again, Kamal. So I think in the interest of time, we have a long session today with our stellar collection of speakers here. So we could move on to the next speaker. Thanks, Kamal.
Thank you. Thank you once again to all the committee members and organizing committee. Yeah.
Thank you. So bring on to the stage now my friend Maja Rücker. Maja, are you there?
Yes.
You are here. You're here. Good. Wonderful. So Maja is an assistant professor at the mechanical engineering department at TU Eindhoven and is a visiting researcher of the Max Planck Institute for Polymer Research. Starting her career in petroleum engineering, she's now gradually transiting towards the development of porous materials for energy technologies. She was also one of the founding members of the Interpor Student Affairs Committee, the Interpor Equipor Initiative, and the Porous Media Tea Time Talks. And Maja, it's as we all know her quite well, and it's a tremendous driving force in the porous media community. She's not only good at doing things, but she's also very good at engaging and motivating others to do things. And like this very channel is a direct result of her, of the way that she is. So we are all very grateful to you, Maja, for everything that you have done in many ways for us and for the community. So
thank you very much for the very kind introduction, and it's always a pleasure to be at Porous Media Tea Time Talks, and of course also with Interpor. Yeah, so yeah, thank you very much for having me here. Good. So I will start with the presentation as well, and I have little comments on community later on, and I'm happy to have a chat about that in greater detail. Yeah, so my talk today is about porous materials for energy technologies. And those who know me, they know that I studied geosciences. So the first porous material I worked with was rock. And yeah, this is basically my work, majority of my work. Yeah, so what you see is fluid transport in porous rock. We talked about already with Kamal about wettability. And this graph is actually showing the impact of wettability across different length scales. At the very top here, yeah, at the very right end, you see the relative permeability saturation relationship, which is the interplay of different, which reflects the interplay of different fluids on transport across the Darcy scale, and this is the term that you actually use in application. So this is what you plug into reservoir models to understand a bit better how your reservoir develops as you replace different fluids within them, like for instance during hydrogen injection. This is a notoriously difficult measurement. You need to core the rock from the underground, which is of course which you need to then restore to the conditions it was in, and then the experiments are also not easy and usually very time consuming, which caused a great effort into finding digital solutions to replace this measurement by digital means, which gave rise to digital rocks physics. And the question was then, okay, well, we have the relative permeability saturation relationships at the larger scale, but how can we use our understanding of the fundamental processes behind it to actually create a digital reassembling the experiment digitally. And yeah, so this is basically what was the scientific question, and we used a mixed bottom-up, top-down approach, how our industrial partners used to call it. bottom up, meaning that we really start with the challenges which we see in the measurement. So we start with the experiments as they are done in the discipline, and then we break it down to the actual physical limitations and try to resolve the issues which are pending for the digital models from that. Yeah, so we use fundamental knowledge, but we are actually directly targeted it to the application. And this, I think, was an important learning as well, conceptually, because when we're now targeting other materials, so when we go towards other sectors within the energy industry, trying to get the industry towards more sustainable applications, we can think of photovoltaics, nuclear power, fracking, geothermal, electrolyzers, batteries. Yeah, in all of those applications, we find porous materials, and they have challenges, and we have great understanding of the fundamentals behind it from our observations in nature, or our observations in the reservoir. And we can use this knowledge, this fundamental understanding, to target the issues which they find in this particular applications. And in a recent review with some colleagues, we actually broke it down to different processes which we are observing. So one which we are particularly keen in reservoir modeling is mass transfer. Yeah, it can be multi-phase flow, as the one discussed, but also reactive transport. Can be charge transfer. Yeah, so if you have porous electrodes, for instance, heat transfer for insulation applications, radiation transfer, if you want to directly convert solar power into molecules, power to X technologies, but also, of course, mechanical stability, which is tightly related to pressure transfers, which you have in porous materials. And all these different processes are actually impacted by the porous structure, which is multi-scale. Yeah, so you have different pores which are contributing to each of these different processes by different means, meaning that we have the same challenges as we have in reservoir engineering. We have a multi-scale problem. We have different processes which are coupled, and we need to find a way to resolve them all in once. And yeah, what I'm going to show you today is a slightly different application from rocks, which is a ceramic membrane which is used for hydrogen separation. And this membranes, they need to be very thin. Yeah, so you want them to separate, but you don't want them to stop the entire reaction. So you have them very thin so that they transfer only the desired hydrogen, but don't reduce the transport too much. So very thin membranes are very difficult to manufacture if you want to do this in size, yeah, in big sizes. So if you want to scale up, which is why you support them with a porous structure. Yeah, so you create a porous layer on top of a very thin layer, and this causes then again a problem when you try to heat it up. Yeah, so we use, for instance, so in this application, particularly ceramic membranes, because they are structurally very stable, or can be very stable if they're manufactured well. But when you have this bimodal distribution, what happens when you heat, or what can happen when you heat it up, that it bends. And this is, of course, something which you do not desire. So we looked into what is the driving force behind this bending, and this is in principle the interfacial tension, the relaxation of interfaces. Yeah, so if you heat it up, you allow for the molecules to rearrange themselves, and they do so by minimizing the energy required to maintain a particular state, and this is by minimizing surface energy. And I put down here the little bubble, soap bubble, because this is an example on how surface energy minimization can look like. Yeah, you would get a sphere, always a sphere when you try to make a soap bubble. This is because it minimizes the surface needed for a particular volume to be occupied. And similarly, when we observe for the sintering of the ceramic membrane, so this is the powder, and as you increase the temperature and keep it at a particular temperature for some time, then you see that the surface area is getting smaller and smaller, and you see basically the crystals grow bigger and bigger. And here again, with a larger resolution. Now, knowing that the interfacial tension is a driving force, understanding properly the process would mean that we would be able to reverse engineer how the ceramic membrane is produced. Yeah, so with this idea, we actually wanted to quantify a bit better how this interfacial tension or the surface energy of the ceramic membrane in particular evolves during time. And the methodology which we use for that is called inverse gas chromatography. An inverse gas chromatograph works inverse to a standard gas chromatograph. You're injecting in a gas chromatograph, you're injecting an unknown gas, and you push it through a standard analytical column, and the preference of a standard analytical column to absorb certain molecules but no others will create a separation of the gases, which then can be used to identify the gas which you inject. In inverse gas chromatography, you use standard analytical gas, so you know the properties of your gas, but you inject it into your sample medium, which can be, for instance, like here, a rock, but it can be also a ceramics, and the separation of the gas molecules tells you something about the property of your porous material. And this is giving you quantitative, not so before we saw the images, but this gives you some quantitative results, like the bed surface area, but depending on the gases which you choose, you can also quantify the dispersive surface energy. So this is the contribution of dispersive interactions, like van der Waals interactions, for instance. With probing with acidic or basic agents, you can get the acidic and basic contribution to the interaction of the solid with a particular fluid, giving you the acid-base surface energies. And this is how it looks like in practice. Yeah, so we get surface energy distributions for the dispersive surface energies for molecules which are dispersive in nature, like the alkane series. We get specific surface energies for polar probes, and we inject them in sequence with pulses getting larger and larger so that they occupy more and more of the surface, with the first molecules landing on the highest energy sites, and then the more you inject, the more you flatten the surface energy. So this difference between the initial injection and the final injection is giving you the distribution of surface energies, and this final point is then the total surface energies, and in this case the dispersive surface energy of the sample. And you see here basically the changes of surface energy for the different temperatures which we go through. So this is the dispersive surface energy. This is the specific surface energy. When you do the analysis, also when you add them to each other, you get the total surface energy which you get. And then if you multiply this by bed surface area, you get actually the surface energy as such per mass. Yeah. And one thing which we see here very clearly is that the energy drops, the surface energy drops as we increase in temperature. Yeah, so this is what we anticipate. But what is very interesting to see is that also the heterogeneity changes. Yeah, so a large part of it is due to changes in surface area, but then there is also here when you look into the distribution, you see that at the beginning you actually have a very homogeneous sample, and then the crystallization causes preferential crystal sites, which have a higher variety on surface energies, which gives you the variability which you observe here at the higher temperatures. Yeah, and then you can break this even down to the dispersive and specific component. So, in conclusion, yeah, to optimize energy applications, we need to account for a variety of transport phenomena occurring at different length scales. Optimizing requires grounding in upscaling possibilities, and so you need to really check what is actually possible in the particular application. An interesting challenge for all porous materials is the limitations due to manufacturing, for which I gave you now an example from sintering, where we looked into the changes in interfacial tension during the sintering process. with a mixed bottom-up and top-down approach, you really manage to couple the fundamental principles with large-scale phenomena. And on the example of sintering, these insights can help you to reverse engineer the processes of surface energy minimization to inform how we need to create the templates to avoid the bending as we see later on. And here at the side, you see, I think I would like actually to highlight Claudio in particular, who did a majority of the experiments which you've seen here. So how? Yeah, so how do you approach actually the energy transition as a community? Of course, is the answer. And this is also my contribution to the question about the well-being and how to manage, because I think it is a real challenge. Yeah, I do believe that most of us recognize balancing the right, how much time you spend on your work, and how much how to separate it from the private life is not as easy. And I wouldn't say that I know the answer. But what helped me a lot was really to talk with people, both about these issues, but also about my science. I cannot say how much it paid back to really engage in the scientific community, like with the Porous Media Tea Time talks, but also with the current initiative I'm working on, the EquiPo initiative, where we try to get people together with the mentorship coming up. So please register for it. But also beyond, so wherever I think community is really important, and really to think of that whatever we do, so in terms of the technology which we are trying to develop, it's for people, right? And the people, and we are working with people, so there's always a human aspect to it, which I do believe should get proper time and space. So us as researchers, as humans, but also the technology which we develop for humans. So I think it's important to talk about community and people. Yeah, and with this, thank you very much for listening.
Okay, first of all, Maja, I have to say that your research is absolutely outstanding. And what I find particularly impressive is that you managed to work across so many disciplines and applications at the same time. As many of us now know, you are very active in the community, definitely within the Interpol, and I suspect far beyond that. And you always seem to be right at the cutting edge of the research. So my question to you is, where does this incredible drive comes from? How do you manage to keep such a good work and life balance, or do you manage to keep it balanced in the current career stage?
I'm not sure whether I don't think that I would be the best expert to ask about how to keep work-life balance. I know that I have the pleasure to work with people who really do. So I struggle. But I know many people which do manage, which I find very impressive. But which also gives hope, and I think that both people should be properly asked about how they manage, because they do outstanding work despite really making sure that it fits into the time you're supposed to dedicate to work. So maybe I'm not the best person to ask when it comes to. But I think if there is something which I would really like to give away, is some experience which I got with the Center of Unusual Collaboration. So this is more towards the interdisciplinary note. So I think one important thing when you try to work interdisciplinary is to recognize that within different communities, you actually do speak different technical language. And this is a barrier, and it is not necessarily that you do not understand the physics, but it's also the way how you operate in your system. So what, for instance, when it comes to how openly you discuss your research, this is very different depending on the community. A fast-pacing community, would be much more secretive about their work, and then you need to clarify also how you feel about it, how you like to work early on, to make sure that this is not going south. So finding common language, finding common way of working is equally important to be discussed. And I'm pointing out here at the moment the Center of Unusual Collaboration, which is researching how researchers research interdisciplinary. And they taught me a lot about how to find common language. So this is the reason.
Any other question to Maja from the studio?
I've got one technical question, Maja. Thank you for the great presentation, as always. This is very interesting with the inverse gas chromatography. I must admit my knowledge is very limited here. What are the uncertainty and the limitations of this technique, like in terms of pore size, structure differences?
So at the moment, I mean, this is, let me here quickly come back. I think the moment inverse gas chromatography, we are able to give distributions of surface energies, but we are not able to specially resolve where these are located. Yeah, so I think this would be the next challenge, to really make sure that we are able to get the energies for a particular location. It would be also interesting to learn more about whether this can be whether the heterogeneity in the sample is something which we can address statistically, or whether this is something which is really a dominant factor, which I believe is true for some contexts, for sure. Yeah.
Excellent. Well, thank you.
Okay, thank you very much, Maja. Now with that, we can move on to our third speaker. I would like to invite our third speaker. I welcome Dr. Tom Bultreys. He's an associate professor at the Ghent University. Tom is a physicist and earth scientist whose research is driven by the fascinating complexity of fluid flow in porous media. From everyday phenomena like water moving through a kitchen sponge, or to large-scale engineering challenges such as storing megatons of CO2 or hydrogen deep underground, Dr. Bultreys explores how fluids, particles, and chemicals interact with the porous rocks. Tom's work and research focuses on critical application for a sustainable future, including geological carbon storage, underground hydrogen storage, and renewable energy, groundwater remediation, and volcanic systems. Tom combines cutting-edge imaging, modeling, and experiments to unlock the hidden physics governed by these vital processes. Please join me in welcoming Tom Bultreys, and the floor is yours, Tom.
Thanks so much for the nice introduction, Mohammed. Yeah, so today I'm going to talk a little bit about one of the main research projects I'm working on, which is X-ray velocimetry. So let me just make sure I can. Yeah, there we go. Yeah, so after these two excellent talks by Maja and Kamal, I don't think I need to introduce flow in porous media anymore. So in my lab, we study fluid flow in porous materials, both on the fundamental level as applying it to underground hydrogen storage, where we actually are involved in a pilot project in Belgium, as well as in projects that are more related to groundwater remediation and volcanic groundwater systems. Now, in all of these projects, we are basically interested in trying to understand how fluid dynamics affect the behavior at the larger scales. And I really choose the word fluid dynamics consciously, because even though a lot of these flows in porous subsurface are very slow, if you start zooming in on the pores, you often see very dynamic behaviors, even fluctuations happening. So that's, for example, the case in multi-phase flow, but it also happens in, for example, viscoelastic flow, where you have turbulent-like behavior at very slow flow rates. Now, that has been studied to an extent using 2D micromodels. Because really the key thing that you want to measure in these kind of cases, if you look at it from a fluid mechanics point of view, is you want to know the flow fields. You want to know how the flow fields are changing over time, right? And so, as I said, that's been studied a bit in micromodels, but really when it comes to 3D porous materials, specifically materials that actually look a bit like the geological subsurface, we actually don't know how to measure this. We don't have methods to measure that. And so we identify that as a kind of key experimental gap that we wanted to work on. So a few years ago, we started working on this method called X-ray velocimetry that addresses that. So today I'll first introduce briefly how that method works. Then I'll show you some examples where we use that to image unsteady flows in porous media. And finally, I will show you what we're doing to be able to measure faster flows than what we can do right now. So just to introduce, X-ray velocimetry, I mean, at least the way we do it, works with particles. And then basically the idea is that just like these ducts show you the flow rate of the river, you put small particles in your flow and you follow them through the porous material to actually measure how fast the flow is locally in your porous material. So we suspend these tracer particles in a liquid, and then we pump it through a porous material. And rather than filming the particles with a normal video camera, we use micro CT, which is a 3D imaging technique. And we make many micro CT images after each other so that we can actually film in 3D where these particles are. And just a note on these particles, the particles we use are quite specific because what you actually want these particles to be is very visible in your X-rays. And to do that, you would basically want to have very big and dense particles. Now, to be a good flow tracer, you don't want that because big and dense particles would sink, they would get stuck in the pores, so it wouldn't work that well. So we find this kind of compromise in metal-coated hollow particles. Typically, we use particles between 5 and 30 microns, and we suspend them in quite viscous liquids to kind of stabilize them. So that currently is still a limitation, the fact that we have to work with these high viscosities. But it is something we're trying to address by building engineering our own customized tracer particles. So once we've suspended these particles in a liquid, which is what you see in this brown liquid over there, how do we then image them flowing through the porous material? Well, as I said, we use micro CT. In micro CT, you take many radiographs across a 360-degree viewing angle, or across 360-degree viewing angles of your sample. And we do that back to back, so time and time again. Each of those blocks of 360 degrees then will get reconstructed into each time one 3D image. So we get now a time series of 3D images. Then we're going to take each of those time frames and we're going to locate our tracer particles in them. So that gives us a number of point clouds for each time frame, or one point cloud for each time frame. And then we're going to link those point detections over time to find the particle trajectories. So that's how the method works. We can apply this method in our own lab. So we have a number of micro CT scanners here in Ghent. We can go down to imaging times of 30 seconds per image. Now, for a micro CT scan, 30 seconds is really fast. But for particle velocimetry, where you're trying to see how the particles move, 30 seconds is actually quite slow. So nevertheless, we show that we can do this, right? On here you see this flow cell. Inside is a small porous sample. And the small dots that you see going through here are the tracer particles. With our tracking approach, we're able to measure the flow fields in porous materials like that quite well. See another video here where we pull out a small, region with a few pores where you can see the particles tracking through. Now, so that works pretty well for relatively slow flows, up to a few micrometers per second. In many cases, we want to track faster flows. And in that case, we actually take this technique and we go to synchrotron. So on the left here, you see an image where we have a acquisition of about 200 images, where it takes about 1/4 of a second to take one 3D image. And this then allows us to make, to do faster tracking for particles up to about 50 micrometers per second at quite nice image resolutions and image qualities, as you can see here on the right. So this is how the method works. Let me now show you some examples of what we've been able to do with it. The first example is a drainage. So it's a low capillary number oil injection into a porous sample, where you will see that on the bottom left here, we'll get a Haynes jump happening. So in a Haynes jump, the fluid is kind of slowly building up pressure and then shooting through a pore. So that happens now. And all the arrows you see are the tracer particles in the oil phase. So you can see that actually when this Haynes jump happens, and it's going to play again now, there's actually a spike in the velocity throughout the entire oil phase in this sample. And this spike is really important because it brings along viscous forces, potentially also inertial forces. And so in our paper in PNAS from 2024, we show that you can actually use this data to analyze the energy dynamics of what's going on in here, as well as the length scales and time scales of these fluctuations. What we haven't shown yet, or not published yet at least, is that we've also got data for imbibition. So the video you're seeing right now, it highlights a snap-off during imbibition on the top there. And when that snap-off happens, we actually also get these fluctuations, which we didn't expect, because snap-offs you would usually suspect are relatively local, kind of small-scale processes. When we actually start quantifying the size of the perturbation that this causes, so the height of the peak in the velocity field, if you want, and plot it in function of the distance to this epicenter where the fluctuation originates, then you see that it actually has a kind of decay, which is characterized by a length scale of about 12 mean pore lengths. So it can be felt quite far away, which is quite potentially impactful in how you model these kind of dynamics. Then finally, if we go to higher capillary numbers, then as some of you will know from previous work from literature, you will get at some point ganglia dynamics. So we've also been able to image that. So what you see over here on the left is a video where we are retracting the oil, right? And you see these oil ganglia starting to break up. Every ganglia has a different random color. And if I play that, you'll see there's a lot of breakup, color changes, movement of ganglia, and so on. So it's really complicated behavior. And we're still trying to analyze and trying to figure out what's going on during this. But let's pick out one of these ganglia, which is actually immobile. And let me show you the tracers in that ganglia and what they're doing. So despite the ganglia being immobile, as you'll see in the video here, you'll see that the tracers inside of it are actually not static. They're actually rotating basically around, forming circular flow patterns inside of this ganglia. And that's caused by momentum transfer. That's exactly the point. So that's what we're kind of investigating further now. So with that, those are all the experiments I wanted to show. I want to just highlight one more thing. This is a collaboration with Gege Wen at Imperial College, where Gege and Chunyang, her PhD student, have developed an AI-based simulator for multi-phase flow, which they train on our experimental 4D velocimetry data. And they show that actually when you do this, you get much better results than when you only train on the fluid distribution images. So having that velocity information there is actually really important to improve performance of these data-based models. And so that's something that is very much early stage work, but it's also very promising. So I'm very excited about that collaboration. Great. And then the last thing I wanted to show you is basically our biggest limitation in the velocimetry right now. And then about 4 voxels per 3D image, then basically what we get in the reconstructed image is a blur, right? And once it's blurred past a certain level, then we can actually not track the particles anymore. So that is actually what's causing this quite low maximum velocity that we're able to track right now. So if we're going back to how we do the imaging, really the critical step where we're introducing this blurring is when we go from radiographs to these time frames. At that point, we kind of coarsen the time resolution by a factor of almost 1,000, typically. So the method we're working on right now is trying to go straight from radiographs to particle tracks without actually doing this time frame reconstruction, which reduces our time resolution and causes this blurring. So I won't go into detail about the method, how it's working too much. I'll just highlight why this is so powerful. The reason is that when we do this, we are actually able to account for the fact that the particle is moving in between different radiographs, right? So rather than getting this blur, we are just fully taking that into account and trying to reconstruct. So I'm going to show you some first results. This is literally from yesterday, so it couldn't be fresher. But we see that doing this, so combining our tomographic reconstruction with our tracking, significantly improves the maximum velocity we're able to track. So we're still working on simulated, let's say, simulated experiments, so simulated tomography data, which does include noise and so on, but it's not real data yet. But so if we have this kind of simulated data where we have particles moving at 20 voxels per scan, if we do our classical workflow on that data, we basically only retrieve very few particles and the ones that are moving very slowly. With our new method, we're able to track much more of these fast-moving particles. And if you look at sort of the histogram of particle detections in terms of velocity magnitude, you also see that. So the classical approach, it drops off sharply after 4 or 5 voxels per scan, whereas the new method is able to track much faster particles. So right now we are really pushing to make this work on our experimental data, and so that it's very exciting prospect to develop that further. So to conclude, for the X-ray velocimetry, it allows us to measure pore scale flow fields in real materials in 3D, which is quite exciting. To do have still quite strong limitations on the speed of the flows we're able to measure and on the fact that we have to use these viscous liquids. But we are working on reducing those limitations, as I showed in the presentation. So that concludes the scientific part of my talk. I did also include well, two short slides on sort of career and well-being. So rather than trying to give real advice, I just kind of put in some things that were important for me, because I think advice is really usually very individual. So I try not to kind of generalize too much, but I can just tell you some things that were important for me. So for me, in my PhD, what was very important, at the very beginning, I wrote a PhD proposal that forced me to read and write a lot and early. And for me, that was really, I think, the basis of almost my entire career. So I would really advise you to try to do that. It's already been highlighted by some of the previous speakers, but we are working with people. And for me, the conferences, especially in the last 2 years of my PhD, were really key defining moments. That was the moment I kind of decided, okay, I want to stay in academia. Because you get feedback on your work, you see people appreciate your work, you make friends, you get inspired. So for me, that was really important. After that, I did postdoc abroad, so I did a periodical for my network as well. So, 2 of the people I worked with there are here today, right? So, yeah, I kept collaborating with these people, and it's been really important for my career. After that, I moved back to Ghent University, and at some point, I did also doubt if I should, stay in academia or go, because we were settled, right, as a family in Belgium, and yeah, I was really doubting. So at some point, I talked to someone who was kind of in a mentorship program, and he will probably advise me to just leave academia, get a real job, so to speak. In fact, he didn't. So when I told him my story, he said, well, one of your main reasons, or probably your main reason that you're thinking about leaving, is the risk of not finding, the position that you want. And he basically told me, as an entrepreneur, that he thought that risk shouldn't be something that you avoid at all costs. So for me, that was probably a good piece of advice. Of course, it depends on how risk averse you are. Right? And at that time, I also started supervising more and more. So yeah, research really becomes more and more about people. And that just keeps, it's important to know that I think at the start of your career, if you want to stay in academia, it will become more and more about people the further you go. And then finally, in 2023, I got a permanent position, which was triggered by a grant I got. And there it became really clear that your success depends on being part of a strong research community. Because as you go further in your career, you start kind of competing more and more with people from other communities. And so if your community is seen as a kind of, passive or not very competitive community, then it will be hard for you to also show that the work you want to do is competitive. So really, I would, say invest in your research community and also celebrate the success within the community, because in a way, we are all successful together, right? And then finally, last bit of advice: if you look forward next few years, with everything that's happening in terms of AI, I think really it's become very cheap to produce large amounts of text, specifically lower quality text. So really, I think quality is what you have to focus on if you want to stand out in that. So that's really something that I would really encourage you. Even if you're in a system where quantity, the amount of papers you publish, is right now still important, I think you can be almost sure that in a few years this will change. Simply because, there is no way to stand out by publishing a lot. You really have to stand out by publishing good things. So, final things. I'm going over time a little bit, I suspect, but this will not be very long. On work-life balance, I think others have also said this. I agree, it's a legitimate issue. Also for me personally, it's an issue. So I don't really have any solutions, unfortunately. What I can say is that try not to look too much at, what works for someone else, right? Don't kind of think, oh, someone else is doing that, so I should also do that. Try to see what works for you, because this is very individual. And also, in terms of working hours, you have a very strong law of diminishing returns. So that 12th or 13th hour you work in a day is going to be much, much less productive than the first one, right? So, don't go overboard in trying to work very long days. It simply doesn't work, I think, at least for most of us. Right? So with that, I would like to thank basically everyone who contributed to this work, and also the funders. And happy to answer any questions if there are any.
Yeah, thank you very much, Tom, for the brilliant work. As always, the research is impressive, and I really enjoy your reflection as well. It's good to hear that people like you also have gone through doubts in their career. And mentorship plays a critical role. I am just relating this that myself as well. So I'm happy to hear that it helped at some point. So I have a scientific question to start with. So you mentioned your time frame reconstruction reduces the resolution in time. So I'm wondering, in your basic approach, how do you link discrete particle distribution to somehow continuum particle path from the very beginning? I didn't really catch that.
So you mean here, basically?
Yeah, for instance, here.
So what we use is what's called iterative tomographic reconstruction. So you basically forward simulate what the radiographs would look like, and then you optimize your output, which is your particle tracks, so that your simulated radiographs match your experimentally measured ones. So that's what the method is based on. Okay,
cool, interesting. So we've got some comments from the audience as well. Mukit Hikbal is thanking you for the presentation and wondering about the customized tracer particles you mentioned earlier on. Are you thinking of micro-sized particle or nano-sized particle?
this is micron size, simply because the resolutions that we can attain, we basically need to work with particles that are a few micrometers at least. Yeah.
Okay. Rima as well asked a question. So during transport, have you observed any structural or size alteration in the synthesized tracer particles that could influence flow regimes detected?
Yeah, sometimes we get particle clogging, so particles getting stuck in the pores and clogging some of the pores. When that happens, we basically call it a failed experiment and retry. So that does happen. You also get sometimes particles sticking together and then getting trapped even more. So yeah, we have to be quite careful with the fluids we use and the way we prepare the suspensions to avoid that.
And then the song is also a member of the T-Time Talk team. Thank you for like being part of the initial round on this initiative. And he asked a question about tracer size of 330 microns seems a bit large. Yeah, it's about what you just mentioned, so collision annihilation.
So how can you make sure that they're really passive? So first of all, we image everything, right? So if they're getting stuck, then we see it. Whether or not if they're not trapped, whether they're impacting the local flow fields, they could in certain cases. Yeah. So we generally work on materials that have relatively big pore sizes. When you go to small pore sizes, then you need smaller tracer particles. Simple as that. Yeah, we also use quite low concentrations of particles, which you might have also seen in some of the images. So that is also to avoid. In volume percentage, we are, having 1 or 2 volume % of the liquid being occupied by particles, and that is also to try to avoid these kind of issues.
Okay. Right. Thank you. Any question from the studio? Yeah, come on.
I've got a very small question, Tom. Thank you for the excellent talk, and also showing the future you're working on, which is exciting actually. Sorry.
Thanks.
Just a very small question related to when you're looking into trapped ganglia and then looking into high velocities. You see the circulations. Are they localized circulations, or they are connected through the ganglia?
So here this is one ganglia. So this entire meniscus you see is a single ganglia, and there you see, if I play the video, you see some very local circulation, and you also seem to have some kind of more global circulation, which you can't see very. It's more suggestion than really proof, but it appears that you get this kind of like circulation across the entire ganglia at some point, which you would have to image longer to really show. But I think it's a bit of both. This is complex geometry, right? This trap blob, so it's experiencing drag along the interfaces from the flowing liquid phase, and that's causing this recirculation. Yeah.
Nice. Thank you. Very interesting. Yeah.
Also, you had a question?
Yeah, so it was actually quite connected to this what Kamal mentioned. Okay. So just to be sure, this what we're showing here is really drag along the interface that is causing this vortices, right? So this is something that's in a very complicated way to happening in 3D, but it's something that you could see in a corner in 2D, for instance. If you have like a little bit of a fluid trapped there, it's going to be turning around due to shear on the interface, even if the whole thing is not moving. This is really amazing that you can image this.
It's exactly the same phenomenon. And we also see that, so this is, I didn't mention that, but here it's viscosity matched fluids. So we actually see this behavior when the viscosities of the wetting and non-wetting fluid are matched, but we don't see it when one of the two has much higher viscosity than the other. Which is also shown before with this corner flow and so on.
That's really amazing. So another quick question. You already touched upon on the last part with the simulated flow fields, but I was just wondering, if you, well, naturally, you cannot track 100% of the particles with 100% of certainty, right? So if you removed a couple of particles from your tracking in 3D, how does that affect the results, in particularly with the peak velocity? You kind of like already hinted at that with the simulated data, but did you try analyzing that with the experimental data, like artificially making the tracking worse to see how that impacts the results?
Yeah, we did quite a lot of validation study when we first developed the method. So we basically created artificial experimental data, so where we basically simulate the entire image acquisition process, and we see what we see in the experimental data as well, so that basically we're not able to track particles if they move beyond 5-6 voxels per scan, right? So let's say 4 to be kind of safe, that you also have a good measurement there. So if you have something that's moving faster, you lose that part of the spectrum. So that obviously biases the results to lower velocities. The other thing we were able to see is that, I mean, at least on the simulated data, we track about 50% of the particles right now. So we're not actually able to track everything, or at least not, you know, we do some filtering and stuff to remove noise, which also filters probably some true detections. So yeah, I mean, anything we can do to improve that is basically a win. And that's kind of what's motivating the last part of the talk that I was showing. So the way we are trying to improve mostly the image processing or image analysis after taking the images.
So this is a PTV, right? Particle tracking. Do you have any hope of doing PIV in 3D?
So the reason why we chose to do PTV rather than PIV is because, well, as I mentioned earlier, we work with quite low seeding concentrations anyway. So in that case, you might as well track your entire particle, because that also, because you don't have to use interrogation windows, you lose less resolution when you do that, which, you know, in a porous medium, I mean, you would basically have almost every interrogation window touching a pore wall, right? So that's why we chose that. Maybe PIV could be useful at some point if we get to a level where we, you know, have tracer particles that are passive enough to increase the concentrations. Could indeed be interesting.
Super. Thanks, Tom.
Thanks for the very interesting discussion. So yeah, I think we are already a bit out of time, but it was a super interesting session, like a special edition. So I guess an hour and a half for 3 speakers is very legitimate. Thank you again to all of you for joining us today. Thank you for sharing your insights about your career, your reflection, and yeah, I really appreciate that from my side, and I guess most of our audience will as well. So just to conclude, I will like to advert our next session, which is next month and back to normal. So we will have 2 early career researchers presenting, Julia Bakalu from Texas Austin and Karol Darbowski from University of Krakow in Poland. So yeah, join us for the last session of this year. And again, so this is our team, our current team. So if you want to just contact us and be involved as speakers, reach out at porosmediattt@gmail.com. And yeah, stay tuned for more enthusiastic talk about porous media sciences. Thank you, everyone. Bye.
Thank you.
Thank you.